working. It's still working. Now, there it is. Let's adjust that setting. Public view. There we go. Now it says we're live. This is odd. Apparently made for kids means I can't. No, stop it. If it's made for kids, apparently I can't do the chat, which is a little unfortunate. Okay. So many buttons, too many things. I want to go to the studio. And I want to go to the streaming thingy. Manage this one. There we go. Okay. I think we're good to go now. So, well, I say that. Almost. Almost good to go. Gotta plug in my whiteboard. Can I really call it a whiteboard since it's all black? I don't think so. Maybe it's a chalkboard. I don't know. Okay, so today what I want to do is a little circuit analysis, which we didn't get to last week because the linear algebra took me longer than I thought it was going to. But I want to start from simple circuits and work up to slightly less simple circuits. And I'm not going to lie, my circuit skills are not as good as I would hope, but I do know how to do some stuff. So we're going to start with Ohm's law, which is the basis for all of the circuit analysis that we do. Ohm's law says that voltage equals current, which we use I for, times resistance. So if you have a simple circuit that has a battery or a power source of some kind and a load that is resistive, if we consider this to be ground, this to be some voltage V, this to be some resistance R, then there's a current flowing with current I, and they're related by this equation. Sounds simple, and it is. So let's suppose that I have a 5-volt battery. So for an example, we're going to have this circuit. So here's another way that it can be drawn. Those are all equivalent, those two circuit drawings. So let's suppose it's a 5-volt power supply and a 100 ohm resistor. Then we have current flowing around the loop, bleh, flowing through the circuit. And if it's I current up here, it's also I current through here and through here and through here, because it's all one loop. I is the same no matter where we are in the circuit in a simple loop like this. Now what that means is we have 5 volts equals some current times 100 ohms. Now if we want the current by itself, all we got to do is rearrange the equation, and we have I equals 5 volts divided by 100 ohms. Cancel out, that's 1, that's 20, and we're left with 1/20th of an amp, which is 50 milliamps. Whoop. I'll write that a little differently. 0.05 amps equals 50 milliamps. And a milliamp is 1,000th of an amp. Which is all well and good, but you're probably looking at that number going, what in the world? What does 50 milliamps even mean? I don't know what that relates to. So let's do another example. Your wall current, or your wall power, is 120 volts. So if you plug a lamp, can I draw please? Plug a lamp into the wall. Did I draw that correctly? Nope. Drew sideways. Plug a lamp in the wall, and you have a light bulb. This voltage is 120 volts RMS, which is root mean square, which basically means if this voltage is DC, then if we plot what the voltage looks like over time, it looks like this. DC voltage, or DC voltage is a little bit overloaded. Maybe we won't call it that. DC power. This is voltage. This is time. This is a constant 5 volts. If we look at this one, then what this one looks like is that, where this value is 120 volts-ish. And I did not include the peaks because the peaks go a little bit higher. But the effective voltage is 120. Now, we use RMS because that is more or less the effective DC voltage. It's close enough for our purposes. So that's what we're going to use to do the math on this circuit. In this circuit, we have to be a little bit fancy. So we're going to use the power law, which we haven't talked about yet. So that's 120 volts RMS. We have some load. It's our light bulb. We've got ground. We want to know what is I. And actually, we don't know what R is either. But what we do know is that the power dissipated in that load is 40 watts. It's a pretty typical light bulb before they all went to LEDs and compact fluorescence. A pretty standard incandescent light bulb was 40 watts. Now we have another law that we want to keep in mind. So we've got Ohm's law. I'll write that up here. Ohm's law. Now we need to look at the power law. Power law. The power law says power is equal to the voltage times the resistance. Star Wars reference. And that's power in watts. We have watts. We have voltage. We don't have current. But we want to know both the current and the resistance. So what we'll do is we'll use the power law to find the resistance, and then use the resistance to find the current. There's a lot of ways we could do it. That's the one we're going to do. So we have 40 watts dissipated by the load equals 120 volts times some unknown resistance. Solve for R equals 40 watts divided by... I totally wrote that wrong. Completely wrote that wrong. That's not times R. That's times current. I don't know, guys. We'll cancel things out. 1, 3, 1/3 of an amp equals 0.33 and so on amps equals 333 milliamps. So that's the thing we're really interested in. This guy over here, 50 milliamps. This guy over here, 333 milliamps. Now, if you've ever touched a 40-watt light bulb while it's been on, or while it's on, or while it has after it has been on for a while, you will discover very quickly that it is quite warm. So 50 milliamps isn't really that much. It's a fair bit, but it's not a lot. This 333 milliamps, that's getting to be a pretty decent amount of current. And just because we can now, if we want to find the resistance of the light bulb, we can say V equals IR. We have 120 volts equals 1/3 amps times R. Solve for R. And you're probably looking at this going, well, 360 ohms is not a lot more than 100 ohms. That's a little more than 3 times. Why is this current so much higher? And the answer is because the voltage is so much higher. 5 volts is not very much. Lithium batteries that you've probably heard a lot about are 3.6 to 3.7 nominally. Sometimes certain flavors of lithium batteries can get up to 4.2 volts, but that's not common and not particularly healthy. and they can go down as low as 3.4-ish volts. Double A's are typically 1.5. Those button cell watch batteries are typically 3. Some of them are 1.5, depending on what you get. So 5 volts, pretty typical logic level for microcontrollers and stuff. Inside of a lot of like Arduinos and such, a lot of that's using 5 volts. 100 ohms is a pretty sizable load for a microcontroller, but nobody's going to get hurt by 50 milliamps at 5 volts. Your 5 volts has to break the skin in order to be dangerous in that case. I forget what the exact amount of current it takes to stop your heart is. It's like 13, 14 milliamps, but in order for the current to break or to get to a point where it's dangerous, it has to go through you, and it can't do that with 5 volts. When you see like Tesla coils and stuff, lightning, Tesla coil. If you see lightning bolts, that means you have a high voltage. Which is a lot of potential pushing on your current. Not pushing on your current. It's a long, it's a high potential difference. You can think of it as like waterfall. I can't speak today. You can think of it as water going over a waterfall. So if you've got a cliff, a waterfall or something, then voltage is analogous to the height of the waterfall. V is analogous to height. Your width of the waterfall is analogous to resistance, and the amount of water going over the waterfall at any given moment is analogous to the current. So if you have a trickle of water from really high up, that's like a lightning bolt. It's not going to do a whole lot. Not a lightning bolt. I don't want to say lightning bolt. It's like a static shock from a doorknob. It's a high voltage, but there's no current there. You can see the lightning bolt from the static shock, but it's not going to do a whole lot. If you see like lightning from the clouds to the earth, that's high voltage and pretty high current. There's a lot of energy there being dispelled into the atmosphere and into the earth, and those lightning bolts carry with them all of that energy. So that would be analogous to a really high waterfall with a lot of water going over it. Your wall power is going to be high-ish waterfall, nowhere near as high as a lightning bolt. And it's going to be fairly wide because you can push a lot of current through your wall power. I think 15 amps or something like that is what the code used to be, at least for your in-house wiring was, which is a far cry from this 333 milliamps. But by the time you stack up a few appliances and such, that adds up. Enough rambling, though. Let's move on to another example. So now we've got two rules that we can remember. We have Ohm's law. Ohm's law. Voltage equals I times R. And if you want a mnemonic to help remember that, I ruined Twinkle Twinkle Little Star for my sister, but you can use the mnemonic Twinkle Twinkle Little Star, voltage equals I times R. And as long as you can remember that R is resistance and I is current, you should be good to go. Then you have power law. Which says power is equal to voltage times current, which is equal to current squared times resistance, which is equal to voltage squared divided by resistance. And these other two forms come from plugging in Ohm's law, and I can do that derivation for you at some point, but I want to do some examples today. So what if we have a circuit like this, plus, minus. What if we have two loads connected in parallel? Then we have some current through here, some I, and through each of those resistors, right? Well, yes, that's true, but we want to be very careful because the current through this branch, I1, and the current through this branch may or may not be the same. But what we do know is that the current coming into this node, this I, and maybe I should make this a little more clear what I'm talking about. The current through this resistor and the current through this resistor have to add up to the current coming out of the power supply. So I must equal I1 plus I2. If you measure these two currents and they don't add up to the same as this current, then you're missing a branch. There's something else out here that you're not accounting for. Or your meter may be causing problems. If you have a very cheap meter, you'll be introducing a little bit of series resistance with each of these, which will bring it down. So these may add up to less than this guy, but not by much. Even the cheap meters will do okay. So this is something that we know to be true about the entire circuit. And then we have how else do I want to talk about this? We have a technique for combining parallel resistances so that R effective is equal to R1 paralleled with R2, which is equal to I'll show you the general relationship. 1 divided by the effective resistance is equal to 1 divided by the sum of the reciprocals of the resistances. Can I stop making things confusing? That would be great. Nope. Let's stop that. It's this. The reciprocal of the effective resistance is equal to the sum of the reciprocals of the individual branches. So what we have is the effective resistance is equal to that. Now, we can do some algebra over here. Do 1 divided by R2 divided by R1 times R2 plus R1 divided by R1 times R2. We're just getting a common denominator. This guy gets multiplied by R2 over R2. This one multiplied by R1 over R1. We're left with this, which gives us 1 divided by R1 plus R2 divided by R1 times R2, which is equal to R1 times R2 divided by R1 plus R2. There we go. So now we can come over here and say, okay, we have voltage. With some current and some effective resistance that we can get as a result of combining those. And this R effective is equal to that guy. So then we can do the same thing. I equals V divided by R excuse me. So we have V divided by R1 times R2 over R1 plus R2 equals V times R1 plus R2 divided by R1 times R2. And that's your current in equation form. This is going to be in amps. Now, what if we start making things a little bit more complicated? Suppose we added another power source, because we can do that. Plus, minus. This is V1, R1, R2, V2. Still relatively simple as far as circuits go. But I want to work through this with you. We can use a technique called, you know what? We can use a technique called node voltage to solve this. Now, let's talk about what a node means. A node is any point with a voltage level. This guy has a voltage level. This guy has a voltage level. This guy, this guy, this guy. All of these places, this whole place down here, has the same voltage level. So it's one node, because it's all connected to each other. This guy is the meeting of three components. So this guy has a voltage. Because it's the same here, here, here. Any place we put our probe in this area, it's going to be the same voltage. We'll call this V2, because V2 right there. We define ground to be our reference point. So if this is V1 coming into the negative side, so the bottom of V1 is 0 volts. We're going to go up to the plus. We've gone up by V1 volts, which means this guy has to be V1 volts. I'm hoping that this makes a little bit of sense to you. It's kind of confusing at first, but you get the hang of it. So what we can now do is we can use the currents to find the voltage. So what we're going to do is measure the current going this way, the current going this way, and the current going this way. So V1 times 0 times 0? Yeah. I times R. So this current is equal to V1 minus 0 volts times 0 ohms, because there's no resistance this way. I'm doing that for my own sake because it's been a while since I've done this. But the current going out of a node, all of the currents added up, will equal 0. Always, period, end of story. That's a confusing statement, but let me try and explain it. If you have a piece of pipe, and we're assuming a perfect world with no leaks, and you have branches off of your pipe, if you've got water flowing down your pipe, you've got some current of water. You can't get more out of your pipe than what you've put into your pipe. And at the same time, everything you've put into your pipe must come out of your pipe at some point. If you just keep pushing water in, eventually part of your pipe's going to explode and let the water out. Unfortunate but true. Electrons in a circuit are no different. If you put them into a node, they have to come out of the node. So everything that goes in must come out. If you're net non-zero, something is wrong probably with your calculations. So now we're going to use that fact to calculate all the values in this circuit. So this is I1. Let's color code, because I can color code. I'll erase and start over with color-coded values and stuff. Color-coded arrows. Here. Measure the current going out, out, going out. Always make sure you're consistent with your arrow direction and your signs on your map. So this is going to be V1 minus 0 volts, because we go from here to here, times 0 ohms plus V1 minus 0 volts, because we're taking the voltage at this side, subtract the voltage from this side, and multiply by the resistance. Is that right? Voltage times resistance. No, it's not. I'm writing it wrong. Aha. Okay. We need to have one more conversation before we're ready to do this. Mostly for my own benefit. When you're doing this nodal analysis using node voltage or later on mesh current, something that you have to do when you're doing it is remember what the ideal impedance of your source is. So with a voltage source, the ideal impedance is infinity. You want to be able to take your voltage source out and this be an open circuit. Because if this has a resistance, if it does this, then this resistance in parallel with the rest of your circuit is going to bring down the total impedance, which is bad if you want maximum power transfer. If you have a current source, which we haven't talked about yet, you replace it with a short circuit, which is 0 ohms, because the more resistance you have in series, the less power you're able to deliver. So we actually get to ignore this one, and I'll show you how. If you do V1 minus 0 volts divided by infinity ohms, because that's an open circuit. Let's use the correct color, please. V1 minus 0 volts divided by infinity ohms plus V1 minus V2, which is on the other side, 0 volts divided by R1. Do this one. So now we're going to do plus V1 minus V2, because that's the voltage on the other side of the resistor, divided by R3, all equals 0. You add all that up, you get 0, because what comes into the node goes out of the node. Now, that means one of these currents, or multiples of these currents, are going to be negative. And that's okay. That just means it's going the opposite direction of the arrow that I drew. Again, which is fine, because I drew all of them going out. One of them should be going the other direction. At least one of them. Now we have to do the other one, because this is only describing part of the circuit. So now let's look at this guy and say, okay, we'll go that way, and that way. Yes, thank you. So now we're going to do V2 minus V1 divided by R3. And notice I'm going in the direction of my arrow. I start at the base of the arrow and go towards the tip. V1 minus 0. V2 minus V1. V2 minus what's on the side, 0 volts, divided by the resistance, which is R2. V2 minus 0 volts divided by infinity ohms. Equals 0. Well, right away, I'm going to say, all right, this guy is divided by infinity. He's 0. This guy, divided by infinity. He's 0. Let's not confuse ourselves any more than we need to and remove unnecessary stuff. So we'll rewrite our top equation. We've got V1 minus 0. Not even going to write it. Divided by R1. Plus V1 minus V2 over R3 equals 0. That one goes up to there. This guy's going to come over here. We'll do V2 minus V1 divided by R3 plus V2 minus 0, not even going to write it, divided by R2 equals 0. Now we have two equations, and if we assume R1 equals yeah, 6 kilo ohms. R2 equals 10 kilo ohms. V1 V1 equals 5 volts. I'm trying to decide what variables I need to have. I think I may have made this a tad simple. I have sabotaged myself. Alright, let's finish. Well, I should be able to do this, right? V2 equals 3.3 volts. 2 volts. R3. We're going to solve for R3 in this case. And I'm not sure why, but we will. So now we got to rearrange our equations. We've got V1 equals, nope, sorry. For this guy, we're going to multiply through by R1 times R3, and we're going to have V1 times R3 V1 times R3 plus R1 times V1 minus V2 equals 0. Solving for R3, so we're going to do R3 equals V2 minus V1 times R1 divided by V1. And over here, we're going to do the same thing, solve for R3. We'll do V2 minus V1 times R2 plus R3 times V2 equals 0. Then we're going to do R3 equals V1 minus V2 divided by nope, not divided by, V1 minus V2 times R2 divided by V2. So now we can use these equations, set them equal to each other. We got V2 minus V1 times R1 over V1 equals V1 minus V2 times R2 over V2. Multiply through by V1 times V2. You got V1 R1 V2 I have too many variables given. V2 minus V1 V1 minus V2 R2 V R2 V2 V1. And now I want to solve for V2 because that's my other unknown. V2 equals question mark. And I picked that arbitrarily, just for the sake of this example. So we got V2 squared times R1 minus R1 V2 V1 equals R2 V1 squared minus V2. This is way more work than I was planning on doing for this problem. R2 V1. Then over here, let's V1. This solving for V2, R1 V2 squared minus R1 V2 V1 minus V2 R2 V1 R2 V1 squared R1 V2 squared minus, we got a V2 and a V2, and that needs to be a plus because we subtracted it from this side, so we got to add to both sides. That's plus. So then we're going to do V2 times R1 V1, nope, R2 V1 minus R1 V1. Minus R2 V1 squared equals 0, and then we use the quadratic formula. I'm going to cheat and use a calculator. It does that. R1 V2 A times x 2 plus e times y minus times x minus b times y to the 2 x. Okay, so there's two possible solutions. V2 is equal to, this is not the problem I was hoping to work for you guys. I did not carefully choose my example. Negative R2 times V1 divided by R1 over V2 equals V1. Both of those seem reasonable. And actually, okay, I'm cool with both of those answers. If R2 and R1 are equal, then these answers are the same. If they're not equal, then these answers will be different. R1 and R2 are not the same, so those guys are going to be different. that true? Yeah. Yeah. R1 and R2 are not equal, therefore we will use this one. So now we use an equation. R3 equals V1 minus V2, but we're going to substitute negative R2 V1 over R1 over R1 equals V1 over R1 minus plus R2 V1 over R1 squared equals V1 times R2 over R1 plus R1 squared. V2 we can actually plug in because we've got values, right? R2 is 10K, negative 10K, times V1, which was 5 volts, divided by R1, which was 6K. The K's cancel out. We can cancel out a 2. And we're left with negative 25 volts divided by 3. Which is about 8 1/3. This guy is 5 volts times 10K divided by 6K plus 6K squared. I combined wrong. And the easier way to do it is just 5 volts minus negative 25 thirds volts over 6K equals 15 plus 25 over 3 by 6K volts. That's gonna leave that. That's ohms. $40 over 18 ohms. Is that right? Yeah. What? My units work out? Yeah. Volts minus volts divided by resistance. Oh, times R2. R2 was okay. Yeah. Negative 10. Nope. Times times 10k ohms. Tip, always make sure you copy the entire problem. Yeah, so now we got 5 volts divided by 6 kilo ohms plus 25 over 3 . No, it's going to be 250 divided by 3 times kilo ohms. So that's volts, bugger. I'm putting my parentheses in the wrong place. Or not enough of them. This whole thing gets parentheses. That whole thing gets parentheses. Come on. Volts. So the kilo ohms cancel. I'm left with a 5 and a 3 here. And so I have 40 over 3 volts inside times 5 divided by 3. Gets me to 200 over 9 volts. That's 20 something. I must be getting sick or something. My algebra's not working right. 200 divided by 9. 22.2 volts. Not volts. Not volts. What am I doing? Volts in here. Volts divided by volts. Goodness gracious. That's not R1. Let's just, yeah, start that whole mess over because that was not correct. R3 equals V1 minus V2 divided by V2 all times R2. That will give me ohms. Goodness gracious, I'm so sorry. V1 is 5 volts. V2 is negative 25 thirds volts. 25 over 3 volts. All of this times R2, which was 10 kilo ohms, equals 40 over 3 volts divided by 25 over 3 volts. Well, the volts cancel. The over 3's cancel. I'm times 10 kilo ohms, and I'm left with 40 over 25 times 10 kilo ohms. That goes to 8. That goes to 5. 5 cancels with that one, and I get 2 and 1, and I'm left with 16 kilo ohms. So V2 equals negative 8 1/3 volts are 3, not 2, equals 16 kilo ohms. And that took much more time than I was expecting to spend on this. And while I would like to work another one and actually show you node voltage properly, because this was not it. It was the long and hard way of doing node voltage, which I mean, I guess it technically still was node voltage. But there's a shortcut that you can do with your calculator that I want to show you next week. So tune in next time to see node voltage on a calculator, and maybe mesh current as well. And I'll try and brush up on my circuit analysis so that I don't make all these mistakes again. But if this was interesting, if it helped at all, be sure to hit the like button and subscribe for more. It's not always circuit stuff. Sometimes I do straight math. I want to get back into doing some differential equation stuff, some calculus, and all of the fun stuff. Also do a lot of robotics projects. So if any of that is interesting to you, be sure to subscribe. Join my Discord if you have homework problems that you want me to work. I am open to suggestions. YouTube chat isn't particularly conducive to sharing math problems that you want me to work, so I have a Discord server. So if you join that, put your problem requests in one of the many categories there, preferably public whiteboard, if not in one of the specific categories. I am competent in many areas of math, and I'm getting rusty. So this is my way of helping other people with their math problems and also staying up to date and well practiced. So I guess that is it for me, and I will see you guys next time.